Hello, in this video we study Taylor polynomials and we'll see how polynomials functions can be used as approximations for other elementary functions. Actually, we already worked with such approximations before in calculus 1. Okay, let me remind you about that. The first is when we studied area problem, right? So suppose that you have some function y equal to f of x, and you want to find the area of the region enclosed by the graph of the function on some interval a and b, right? So basically you need to find the area of this region. So go back to that topic. Firstly, we need to do some partition, right? And then, you use rectangles. Is that correct? You use rectangles. So, okay, let's choose the left endpoints. How about that? So I choose left endpoint, and then in the second interval again, I choose the left endpoint. So basically, I have, these rectangles, and then we sum them up, right? And we take the limit, and we get the exact area, okay? So we know definite integral from a to b of fx dx is equal to limit of the Riemann summing here. I write Riemann sum fxi. I run from 0 to n minus 1, okay, delta x, when n approaches infinity. We use left endpoint, so that's why we have, the index I runs from 0 to n minus 1. All right. So how to see approximation in here, right? Actually, we already consider limit in here. But how to see, approximation for function y equal to f of x? Actually, we use the following approximation. We use constants, right, to approximate the function. So how to see that? Look at this. Look at the first piece in here, right? Here's the first piece in here. Let me zoom this out. Okay, let me draw another one. So that's the first P. And I use this rectangle. So basically, I use this constant to replace the curve of the function on this interval. Does that make sense? So, yeah, what is this? Since this guy is a, is just x0, the first one should be f of x0. So I write, yeah, f of x is approximately f of x0, right? Around, all right, in the neighborhood of of a, which is a equal to x0. So basically, I replace, instead of considering the function right here, I just consider, the constant. And then for the next interval, again, I choose another constant, right? I choose another constant, and actually that is f of what? F of x1, and so on. Does that make sense? So, if we look at this picture from point of view of approximation theory, yes, we already use this approximation. We use scalars, functions, to approximate our function. Or sometimes, we say, yeah, that is step functions, okay? Because, the function looks like steps, like here. First step, and then second step, and so on, and so on. Does that make sense? All right, so that is the first approximation, and probably you might not pay attention on this when we study integration, okay? The second approximation case we learn in calculus 1 is linear approximation. Okay, so what is linear approximation? You have some function y equal to f of x in here, right? You consider some point, let's say that is x0, okay? And then you consider the tangent line to the graph of the function at that point. So in a very small neighborhood of x0 in here, you may replace the function by the equation of this tangent line. So that's why you have linear approximation. Okay, let's write the equation of the tangent line. Y equal to f of, okay, f prime, right? The function is f of x. Okay, without the arrow in here, sorry. We don't have the arrow in here, okay? Oh my goodness. I don't have this. Okay, and then times x minus x0 plus f of x0. So we replace the function f of x by the equation of this tangent line. So f of x is approximately equal to fx0, x minus x0 plus f of x0 here. Let me rewrite this equation, okay? This approximation line, f of x is approximately equal to f of x0 plus f prime x minus x0. So, interestingly, if you compare this approximation and the one we just discussed in here, you see, in the first one, you get f equal to f of x0. You see that? In the second one, you add one more value in here, f prime x minus x0, and you get a linear function. Actually, this is polynomials, right? Is that correct? So you see, look at this, right? This is linear approximation. Why linear? Because you use linear function. And that is the equation of the tangent line. Does that make sense? So these are two cases we learned in calculus 1. Approximation. The first one in integration theory, we use, if you use rectangle, so that is, constant approximation, let's say that, right? The second one, you use tangent line, so that is linear approximation, okay? So you might ask me the question, may we use quadratic approximation or may we use polynomials with a degree higher than 1 to approximate the function? Of course, we might do that. Does that make sense? Actually, we already did that in calculus 2 when we use Simpson approximation, Simpson formulas, when we study numerical integration, right? That is quadratic approximation. Okay, so that is quadratic approximation. When we approximate function using quadratic functions, quadratic polynomials. Okay, so that means we may use, polynomials of high degree for this purpose, or maybe for other purposes. Agree? And that is the main, topic of this section. All right, so let's consider some examples, right? Let's say we have function f(x) equal to e to the x. We want to consider the first degree polynomial function, right? p1x equal to a0 plus a1x to approximate e to the x, okay? And you consider the point x equal to 0. So basically, this is linear approximation, right? So for that purpose, I need to differentiate. I need to find the tangent line, right, to the graph of this function at 0. That's it. So I find fx prime okay, that is e to the x. And then from here, I can find the slope is equal to e to 0, which is 1. And I know f of 0, that is e to 0, again 1. From here, I get the equation of the tangent line. So that is y equal to, the slope is 1 times x minus 0, right, plus f0. From here, I get y equal to 1 plus x. Then, e to the x is approximately equal to 1 plus x at 0. So this is my linear approximation. Okay. So let's move to, higher order polynomials, right? Which they give you another estimate, of function e to the x. Okay. Let's move to quadratic, right? Approximation. So that means I need to find some, quadratic function f2x equal to a0 plus a1x plus a2x squared, okay, which is an approximation for e to the x. Of course, you might think, yeah, actually the first two terms, a0 and a1, right? We already found that in here. Is that correct? So basically, I can think, yeah, we need to find a2 such that e to the x is 1 plus x, and then a2 x squared. So how to find a2 in this situation? All right. So, since we have this approximation, I might differentiate both sides. Okay, if I differentiate both sides, so I have the following one. E to the x is the left hand side is again approximately equal to 1 plus 2 a2x. Is it right? Because derivative of 1 is 0, derivative of x is 1, derivative of a2x squared is 2a2x. But we still don't have a2, right? Since this is true for every x. So I differentiate one more time, right? Is approximately equal to a2 for every x. Right? Oh, by the way, yeah, not for every x. So I think we are talking about x equal to 0. Sorry for that. We are talking about x equal to 0. I should write here, around 0, right? Around x equal to 0. So you look at this. E to the x is still e to the x. Is approximately equal to a2, right? Around x equal to 0. So when you plug x equal to 0 into this, you see e to 0 is approximately equal to a2. Or a2 is, okay, let's say 1 over 2. Then I plug this into my quadratic polynomial, right? From here I get b2x is equal to 1 plus x plus 1 over 2 x squared. You see that? So I have another approximation. This is approximately equal to e to the x. Of course, you might have a feeling that when we increase, right, the decrease in here, so we get more exact approximation. Is that correct? And that is true. Let's develop this technique to get, the third degree polynomial approximation for e to the x. Okay? We just, generalize this, technique. Now I want to get some b3x equal to 1 plus x plus 1 over 2 x squared plus a3x cubed, right? Because I already have all these terms. Is that correct? So again, similar to this case, we need to differentiate how many times? 3 times, because you have x cubed in here, right? You need to differentiate 3 times, so x cubed will disappear, and then you get a3. Agree? Okay, this is approximately equal to e to the x. Let's differentiate 3 times. When you differentiate 3 times, these terms will disappear, just 0, because x1 and x squared, so you care about this term only, okay? So the first term of differentiation gives me 3a cubed x squared. Again, that is approximately equal to e to the x. In here, I just move to the second one. Of course, you know, the first time we still have the derivative of this part, right? But as I said, we need to do that 3 times. So yeah, in here I have second time 6a3 x, okay, and one more time this gives me 0. Here I have 6a3 approximately equal to e to the x at x equal to 0. Then I plug 0 into this, I get 6a3 approximately equal to 1, or a3 equal to 1 over 6. Okay, so basically, you know, look at this. We write 1 over 6, right? But if we pay attention, now the first integration in here, differentiation in here, I have 3. The second one, I would write in here 2 times 3. Okay, that is 6. Is that correct? And the next one, you know, the power in here is just 1. You see, the power of x is, you know, decrease from 3 to 2 and then to 1. But each time when you differentiate, you know, you take the power down. So you get 1 times 2 times 3 in here. That is still 6. But I want to write 1 times 2 times 3. So basically this is equal to 1 over 1 times 2 times 3, which is 1 over 3 factorial. Does that make sense? All right, now I will compile everything. I get p3x is equal to 1 plus, I write x over 1 factorial plus x squared over 2 factorial plus x3 over 3 factorial. This is approximately equal to e to the x. Does that make sense? So you may again generalize this technique, right? And you want to get, you know, some polynomial of degree n, which is an approximation for e to the x. You may guess, yeah, that is what? It's 1 plus x over 1 factorial plus x squared over 2 factorial plus so on plus x to the n over n factorial is approximation of e to the x. Of course, this happened at x equal to 0. So I hope that you enjoy this example. Now let's talk about general case when we expand a function at some point. Okay, because you know in this case we have approximation for e to the x, but that is about x equal to 0. So what happens if we move from 0 to another point? Okay, so that means I need to find a polynomial p and x. Again, this is equal to a0. Okay, let me write b0 plus b1x plus b2 x squared and so on plus bn x to the n. And such that, you know, p n as c is equal to e to the c. Okay, and of course, you know, p and x is approximately equal to e to the x. So that is our purpose. Look at this. So what happens if you plug c, right? If you plug c into this polynomial. So that means, you know, you have, you know, c in here, c squared in here, and c to the n in here. So it is very complicated, right? It's, you know, that's not very pleasure. So sometimes, based on this observation, I would say I just want to have only one term when I plug c into this polynomial, right? So that is, I just want e to the c. So I want exactly e to the c is equal to b0 in here. Okay, so I may write my polynomial p and x in the following form. I want to see p and x in the form a0 plus a1 x minus c plus a2 x minus c squared and so on plus an x minus c to the n. Because in this case, you know, when I plug c to this polynomial, I just get a0. And that is exactly equal to e to the c. Because, you know, all the terms are just 0, you see? Which is good. Does that make sense? So we try to find a polynomial Pn in this form. Okay. First, we have, a0 equal to e to the c by just substituting x equal to c into the polynomial, right? Next one, we might differentiate. So we just copy the argument we did for this example, right? So we differentiate, and now we differentiate n times, okay? So the first time, let's say Pn prime c equal to a1, because in this situation, a0 disappears, right? a1, derivative of x minus c is a1, okay? It's just 1, sorry, so you have coefficient a1 in here. The second coefficient is 2a2 and x minus c plus so on, plus n, an, x minus c to n minus 1. Oh, sorry, here you should have p n to the x, right? We just differentiate it. And now we plug x equal to c again, right? So we have Pn prime c. You can see that is just a1 because all the terms are 0. Because you have x minus c, right, in other terms. So you see, it looks very nice. Is that correct? So if you do differentiation one more time and you plug c into the derivative, the second derivative, you get very similar. Look at this. So let me differentiate it second time. a1 derivative is 0. So I have 2a2, right? X minus c. Okay, we don't have x minus c anymore. Plus 3. Because here, if we just copy, the third term, I have a3, x minus c3. You differentiate one time, you get in here 3a3, x minus c square, right? You differentiate one more time, you get 3 times 2, a3, x minus c, and so on. Does that make sense? I don't care about these terms because, when I plug x equal to c into the second derivative, I get 2a2. From here, I get a2 is equal to Pn second derivative sc divided by 2. Okay? So let me mention these are coefficients. If you do one more time, right? And then let's do that. And then we generalize. You differentiate this one more time. You have, the third derivative x. From this term, you get just 3 times 2 times 1, a3. Other terms, I can write x minus c with some, qx. How about that? Because other terms have the common factor x minus c. Does that make sense? So I just plug c into this derivative. I found that is 3 factorial a3. Other terms are just 0. From here I get a3 equal to Pn second derivative c over 3 factorial. That is the coefficient a3. So I hope you may guess, right? The next term would be a4 equal to Pn, the fourth derivative, c over 4 factorial, and so on. An is Pn, derivative of the n, c, and then divide by n factorial. Now you plug everything, right? You substitute everything into the polynomial Pn, right? The coefficient right here. Okay, not in this. Okay, we are working with this, so I get the following one. Pn is equal to e to the c plus derivative of e to the x, with any order would be just e to the x. So equal to the first derivative sc divided by 1 factorial x minus c plus second derivative of c 2 factorial x minus c square, okay, plus so on, plus Pn the nth derivative sc over n factorial, and here we have x minus c to the n. Now we just find derivative and then plug that into the formula. So we get e to the c plus e to the c over 1 factorial x minus c plus e to the c over 2 factorial x minus c squared and so on plus pn and, okay, sorry, we can write e to the c over n factorial x minus c to the n. You see, and that is what? This is approximation for e to the x. You see that? At any point c. Okay? This is approximation for e to the x at the point x equal to c. And this polynomial is called the Taylor polynomial. Okay? This is the Taylor polynomial for e to the x at x equal to c. And when x equal to 0, I mean when the c is 0. So this Taylor polynomial is called the Maclaurin polynomial, right? So basically, you know, general form, yeah, at any point is called Taylor polynomial. But at 0, that is called Maclaurin polynomial. Does that make sense? So the one we just obtained previously, this is Maclaurin polynomials, right? And right now we have, you know, Taylor polynomial for e to the x. I especially did, you know, this argument because I want to generalize for any function. You know, we may obtain this formula, you know, based on the Maclaurin polynomial for e to the x. Agree? Let me show you that before we move to general functions, okay? You know, we may apply this formula, right? Okay, let me copy this. I just want to show you another proof, right? We don't have to do all this for e to the x because we already have that. So I put x equal to x minus c. Okay, x capital equal to x minus c. So when x is equal to c, you know, x capital is 0. So that means we might apply this formula for the x capital. How about that? So I have e to the x capital equal to 1 plus x over, I'm sorry, here should not x, right? X capital over 1 factorial plus x squared over 2 factorial and so on. Let me approximate equal to plus x to the n over n factorial. But x is equal to x small minus c, right? So, and then, you know, I plug x small minus c in here, I get e to the x small minus c approximately equal to 1 plus x minus c over 1 factorial plus x minus c squared over 2 factorial and so on plus x minus c squared n over n factorial. And now, you know, what is x to the e to the x minus c? You know, that is just equal to e to the x divided by e to the c, right? You copy just all this. And then you multiply both sides by e to the c. You get e to the x is approximately equal to e to the c plus e to the c x minus c over 1 factorial plus x minus c squared. Okay, here I should have e to the c, right, over 2 factorial plus so on plus e to the c x minus c to the n over n factorial. That's what you got exactly here. If you compare these two formulas right here. And then with this one. Does that make sense? All right, now let's talk about general, right, function, or about Taylor polynomial and Maclaurin polynomial for general function. Suppose that I have function y equal to f of x, and this function is differentiable. Okay, f of x is differentiable with any order. Okay, the reason we want that because we want to get to take the derivative of the other n. Then f of x is approximately equal to f of c plus f derivative as c over 1 factorial times x minus c plus f second derivative as c over 2 factorial x minus c squared plus so on plus f to the n as c over n factorial x minus c to the n. Okay, and this is Taylor polynomial. Okay, again, when c is equal to 0, we have Maclaurin polynomial. The proof is almost the same for the case e to the x. Okay, now let's apply that technique right here, right, to find the Taylor polynomial for the function ln of x. So basically, we need to find derivative of the function and derivative of the n, right? So that means we have to differentiate n times. Okay, all right, let's do that. Let me write here. Basically, we need to find derivative of the function, right, of other n for any n. That's it. So if you have y equal to ln of x, let's say the first derivative y prime is 1 over x. I can write x to negative 1, right? The second derivative is negative x to negative 1 minus 1, which is negative x to negative 2, right? The third derivative, sometimes we need to try, a little bit before we guess the general form of the derivative. So the third derivative is equal to negative 1 times negative 2 times x to negative 3. It seems like we already close to the general form. Okay, let's do that one more time. The fourth derivative is negative 1 times negative 2 times negative 3. You see that? And x to negative 4. So you may think, yeah, y n derivative, right? That is negative 1 times negative 2 times negative 3 and so on times negative should be n minus 1. Is that correct? You see, here we have 4, right? And here you have 3. So here you have x to negative n. So how to rewrite this term, right, in general form? I would write like this. I would take negative 1 out. So I have negative 1. How many times in here? It should be n minus 1 time, right? Is that correct? With the negative 1. So I write negative 1 to the n minus 1. Does that make sense? And then times the remaining part should be 1 times 2 times 3 and so on times n minus 1. And here I have x to negative n, right? And then, that is negative 1, n minus 1 factorial times x to negative n. That is my, derivative of the other n. Looks good. Now we just plug c equal to 1, right, into the derivative. And then we write the formula. That's it. You see when x equal to 1 in here, so everything looks good. The n derivative at 1 is negative 1 to n minus 1 times n minus 1 factorial. Because, this term is just 1. Okay, I think now we are ready to write the Taylor polynomial for ln of x. Taylor for ln of x at x equal to 1. Or sometimes we write centered at 1, okay? So that is p to the nx. The value is ln of 1. The function, you see that? Just copy the formula right here, okay? F of c. And then, derivative, and then x minus c. So, and then, let me write here, plus the first derivative, y prime at 1 over 1 factorial x minus 1 plus y second derivative at 1 over 2 factorial x minus 1 square plus so on plus y n derivative at 1 over n factorial x minus 1 to the n. Okay, that is your Taylor polynomial, right? For ln at x equal to 1. Now we just plug all this. So we get Pn x is equal to 0 because ln of 1 is 0. The first derivative, where's the first derivative? Oh, actually we can use this formula. Let me see. When n is equal to 1, right? So this is 0. 0 factorial is just 1, right? And here negative 1 to 0 is 1. So 1 over 1 is just x minus 1. That's the first term here. Let's move to the second term. When n is equal to 2, I plug n equal to 2 again into the general form of the derivative. I get negative 1 to 2 minus 1 means negative 1 to 1, which is negative 1. And then 2 minus 1 factorial is 1 factorial. That is again 1, right? So I have negative 1 or negative 1 divided by 2 factorial x minus 1 square. And so on. I think you might think like, negative 1, that is some alternating series, right? So you have, here you have 1, next you have negative 1, and then next you would have 1, right? But the factorial will change. Look at this. Okay, let me write here. General term is negative 1 to the n minus 1 in here. At 1 we already have that. So n minus 1 factorial divided by n factorial x minus 1 to the n. It looks really good. You see that? It looks really good. Look at this. So that is, x minus 1 in here minus x minus 1 square over 2. You see? Plus so on, plus negative 1 to n minus 1. N minus 1 factorial simplify with the n factorial. That is just, n. And here I have x minus 1 to the n. Does that make sense? Is it? So if I write, general, right, series in terms of sigma notation, I have the following one. Pnx equal to I from 1 to n negative 1 I minus 1 in here, and then x minus 1 to the I. Does that make sense? Again, right? We call Taylor polynomials Maclaurin polynomials, and we use those polynomials to approximate the function. Right now, we don't do any approximation, right? But we understand the idea about that, because you move from constant to linear to quadratic, and then any polynomial of degree n. But basically, what were we doing in this video? If we know the formula, the general formula right here, then it turns out that in order to find Taylor polynomials or Maclaurin polynomials, we just need to differentiate the function. So we need to find the general form of the derivative of order n. That's it. Does that make sense? So again, terms are terms in calculus 1. But the idea is again is a little bit advanced than calculus 1. Alright, so I hope you enjoyed the video. I will stop my video in here. I will make another video on Taylor polynomials and approximations with other examples. Right? Bye bye.